everyone. Okay, so let's start with the attendance. Crystal, Young, Sion, Angelia, Cooper, Vin, Perry, Harrison, Lucian, Logan, Gary, Ray, Eric, Olivia, Curry, Jason, Aaron Jesus, Kratos, Romeo, Yuri, Johnny, Andy, Trey, Leon, Zenon, Jason, Terry, Link, Marvin, Peter, William, Pauline, Willow, Cindy, Penny, Hugh, Luang, Murphy, Ziegler, Carvin, I got it. Carl, Coleman Lee, Henry, Zach, Colonel, Lucas, Andy, Bob, Scott, Ken, Anthony, Maxwell, Charles, Phoenix, Harry, June, and David. Okay, I saw last night, you guys are not enrolled, not too many students are enrolled in groups. We will be starting presentation next week. Probably, I may have one extra class for you guys because you are a little bit behind. Other than that, we'll finish the course. So, the important part of your course is group presentation and group project report, right? And it's 15% of your total score. For some reason, students are not enrolling in groups. Where you can find it under people. When you go under people, there are 50 groups, and you can enroll yourself over there. Because next week I'll be giving you the project presentation schedule this week. So please try to enroll it today. Okay, make groups and enroll today. Because I mean, why will you lose at least 13, 14 points out of 15 for your final score, right? You will not want to lose that. So get yourself enrolled in the groups. I have created, when you go to Canvas, go to people, you will find the 50 groups. You can enroll in any of the groups. Okay, under people, in Canvas, enroll yourself. Okay, so I'll schedule the presentation for next week. I'll be sharing the presentation schedule this week. Everyone, right? So we'll try to finish this course this week, or not if this week, then next week I'll arrange one extra class for you guys, because we are left with one chapter after this. Okay. Okay, so let's start. I think we left here last time. So statistical model of quantization errors. Well, we can model quantization error like this. We have this input to the quantizer, and there is an output of the quantizer. We have this quantization noise. So in statistical, if we are making a statistical model of this, we can have this E of n, which is quantization noise here. So a simplified but useful model to analyze the effect of quantization error is shown here, right? The error introduced by the quantizer are represented as an additive noise signal. So here, this is the model. Now, there are certain assumptions when we do modeling, right? We do certain assumptions. So assumption number one, the successive noise samples En are uncorrelated. If they are uncorrelated, that means, well, samples, right? Noise samples, they are uncorrelated. They are independent from each other. They are ID, right? So in that case, it will constitute a white noise, just like white noise, right? Similarly, this error signal, E of n, quantization noise, this is uncorrelated with the message signal. So these are the assumptions. Now, for rounding quantizers, all small deltas, the number of levels m large, it is reasonable to assume that the noise sample E of n is uniformly distributed. We are assuming that it is uniformly distributed. And the distribution range, well, what is the range? Range is minus delta by 2 to delta by 2. The maximum is delta by 2 here. So if that is the case, then we can find the variance, right? We can also find the expected value of this. Well, the expected value of this would be equal to 0, right? The expected value here, it will be equal to 0. So now we can find the variance or power of this error. So the power of this error is here, because if we want to calculate that, where it's coming from, what is the TDF, right? What is the TDF of this error? E, the TDF of this error, right? Right here, it's given here. So integrate that. You will find it is delta square f by square divided by 4. Right. Now, if we are using full range is 2V, right? From minus, full range means minus V to up. And full range is from minus V. That is full range. Now we know the relationship between delta and this full range, which is basically delta 2V divided by 2m. So delta is 2V divided by, so we can also write down m. Right. Now plug in this value here, right, into this delta V. So here, plug in this value delta over here. So you got this variance as 2 raised to the power minus 2m v2 divided by 3. Now we need to find out the signal to quantization ratio, quantization noise ratio. The signal to quantization noise ratio is given as here 10 log. In terms of dB, it is 10 log average signal power divided by the average noise power. So let's say the average power, signal power is Px, and the power or the variance or power, talking about the same thing. So here is the variance. So plug in here, you got 10 log 10 sigma square x divided by sigma e square. So then consider an arbitrary signal. Let's say we have the signal x of n, which is less than or equal to x max with power sigma square x. Then assume that the message signal covers the full scale range of the quantizer. Then we put x max is equal to v. So we replace that here. So if we replace that, we got this 10 log 3 sigma square x divided by x square max times 2 times 2m, 2 to the power 2m. Or we can also write down here, here we can expand that. So we got 6m plus this, if we take log of that, right? So if we take log of that, we got 6m plus 4.77 minus 20 log x max divided by the standard deviation in dB. Now look at here, for each additional bit where m is the number of bits, that will increase the SQNR, right, by 6 dB, right? Here, if I choose m is number of bits, so if I increase the bits, let's say if I choose m is 4, so that means I will get this from 24 dB increment in that bit. If I increase the number of bits, each additional increase of bits will increase the SQNR by 6 dB, which is good, right? So now for a Gaussian message signal, let's say we have a Gaussian message signal, x of n is 4 times the standard deviation, and the probability of that is 0.9544. So if we substitute that in our signal, we got, if we plug that here in this equation, so we got 6m minus 7.4 dB. Similarly, if we have sine wave, for sine wave we will get SQNR of 6m plus 4.7 minus 20 log this root 2, which is basically equal to 6m plus 1.77 dB. Now here also each additional bit in the ADC increases the SQNR by 6 dB, right? This m, number of bits, each bit increase of additional each bit will increase the SNR by 6 dB. Example, for audio signals such as music, a high quality representation means preserving frequencies up to 20 kilohertz. Although the Nyquist sampling rate is 40 kilohertz, sampling rate of 44.1 kilohertz in CD and 48 kilohertz in digital audio tape standards are used. Why we use that? For oversampling, right? If we use ideal filter, we are okay with 40 kilohertz Nyquist rate, right? But we do oversampling, practical filters, right? So we'd add 10%. We add 10%, right? So here, if I add 10% to this, I got 44.1 kilohertz. Oversampling, right? Now, we need to calculate the number of bits required per sample if we are wanting SQNR of 96 dB. If that is the case, then here is how we calculate. So SNR, the formula is given. We know it is, just plug in the formula, right? So 96 SQNR, 6m minus 7.25 dB. Well, what is m here? From here we can find m is around 17. So typically 16 or more bits are used to achieve this this SQNR 96, right? The bit rate per audio channel is, well, this is the bit rate, 44,000 samples per second multiplied with this 16 bit per sample, so you get 700 kilo kbps. Simple question. Now we'll talk about what is pulse code modulation. Uh, Here is pulse code modulation block diagram. As you can see here, um, the pulse code modulation, right? So is most widely, well, what is pulse code modulation, PCM? It is most widely used method of analog to digital conversion, where the digital output is represented in a serial bit stream, right? So we are having serial bit stream. If I compare that with parallel, right? Why we do serial instead of parallel? If I do parallel, so what will happen? If I do instead of if I do parallel, right? So if I'm doing parallel, let's say, well, if you remember from your circuit, we were solving some parallel circuit like resistor. So here I have to have two resistance wire, right? I have to have this is one wire, this second wire, this is one wire, right? This is one. So if I'm transmitting data using three physical wire, let's say copper wire, not expensive, but not expensive. So instead of that, if I'm doing this, if I have three, so I'm using just one wire. Right? So I'm sending data over one wire. So I'm sending data, let's say I'm sending 0, 1, 0, 1, 1, 1, 0. So first it will do the first, right? And this will do the second, then third, then fourth, then 5, 6, 7. So they're all coming in a series, in series form. So this one goes first, then this comes, then this comes, this comes, this comes. So one after the other, right? That I want is one after the other. So this is called series bit stream. Bit by bit. We are sending bit by bit by bit, one by one. Before we do the analog to digital conversion, first we have an anti-aliasing filter to remove that detrimental or bad effect of aliasing. So then we have this sample and hold circuit. Well, again, this sample and hold circuit, analog to digital converter takes time to process, right? One sample, then second sample, third sample. So it has this sample and hold circuit will sample and hold the value of that sample so that this converter process it, right? Like if I'm doing this, right? I have this. If I'm doing this, like, can you read it? No, right? So that's what happened inside this analog to digital converter, AD converter. So if it is like this, you can read. But if it's happening like this, well, I cannot read, right? So that's what the sample and a hold circuit will do. It will sample, it will hold the value so that this analog to digital converter process that, capture the value. Once it is done, then then there is quantization and then coding, right? Here it will discretize, and then it will encode that value, and then it will send through the whatever transmission media is. And then at the receiver side, we have the opposite of that. We have demodulator. Then we have digital to analog converter, which will give us back the signal. And then where we have this reconstruction filter, after reconstruction filter, we will get back our signal. Right. So this is what the pulse code modulation is. Now, non-uniform quantization. Up till now we talked about the uniform quantization. So now let's talk about the non-uniform quantization. So here, real audio signals can be transmitted contain both small and large amplitude, while small amplitudes are more loud. Right? We're talking about the signal. We are talking about the speech signal. We're talking about the music. These are real audio signals. Right? So they contain both amplitudes. They contain small amplitude, they contain large amplitude. But more dynamic range. What is that dynamic range? Basically, it is the difference between the loudest possible source, loudest possible sound a system can handle, and the quietest possible sound it can hear. So, what is that dynamic range? So, the dynamic range basically is the here, if I write down dynamic range is basically difference between or smallest possible sound you can. So if I want to write the dynamic range formula, that is 6.02 m plus 1 dynamic range. Again here, every additional bit here will give us that will be so if I want to calculate the dynamic range for 8-bit quantizer, right? So 8-bit quantizer, let's say for an 8-bit quantizer, dynamic range for the level of level and dynamic range of right. So dynamic range would be 8. This is what the dynamic range is. Now, how we do that? Now, how we do this non-uniform quantization? This non-uniform quantization is done by here. How it is done? It is done by a process called expansion. So it's a combination of compressor and expander. Combination of compressor and expander. Compressor and expander. Compressor compress input sample prior to the uniform quantization as the configurant. Expander restores sample with correct relative value. So expand and compress and expand. So here, if you look at this diagram here, we have this nonlinear, it's a nonlinear amplifier, right? It's a logarithmic nonlinear amplifier, and then we get some output y, and then we pass it through the uniform quantizer, and then we got this y of q, and then we pass it through this the result to analog converter, and then at the end we do the inverse of the first process here. So here is my first sample coming in this compressor, which is a nonlinear amplifier. So if I look at this, what is happening here, right? What is happening here at this stage? The small values are amplified, right? So here the small values are amplified, and the larger values are not. Right here, the small amplitudes, they are amplified here. If you look at here, values near the 0, right? They are amplified here, and the large values, large amplitudes are not. Then at the receiving side, at the receiver end, we are doing the opposite. So we are doing the opposite here. So here, the small values are brought back, or they are here, and the large values are here. The opposite of this process is here. So the small values here, they are brought back to their original shape or their original amplitude here. So they are brought back. Then the compression characteristics here, the compression characteristic, well, there are two laws which do this quantization, the non-uniform quantization. One is called the mu law, one is called the A law. Mu law is in US, Canada, and Japan, with mu is 255. Not sure about China, but rest of the world, they follow A law. This is mu law, right? This is mu law. This is mu law equation, and in this is done. Well, this is performed in adopted in US, Canada, and Japan, but the rest of the world they follow A law, mu law, and A law. There's a little bit difference between those. So we choose 255 as standard value. So now for SQNR, this as SQNR for mu law quantizer, it is 6m plus 4.77 minus 20 log 10 log e 1 plus mu. Right. So this 20, this is called the penalty term. This minus 20, this is called the penalty term. Right. This is the penalty. Right. Here, this minus 20 log e 1 plus mu, it is called the compounding penalty term. Right. This minus term called the compounding penalty term. Penalty term. So let's say we are doing an example. Let's say we have the penalty, which is compounding penalty. Right. Again here, each increase of bit will increase, each additional bit will increase the SLR by 6 dB, but again there is a penalty as well. Right. So let's see the graph. So here we have this graph. We have this normalized input, and then we have this normalized output y. So at mu is equal to 0, so it's a uniform quantizer, right? It's a straight line. As we are increasing the value of mu, so you see we are getting curvy, right? We are getting curves which are bending curves. Mu is equal to 5, so a little bit bend. Mu is equal to 100 more bend, and then mu is equal to, let's say, 255. So you have the utmost curve here, which is here. So see here, the values which are near to 0, they are amplified, right? They are amplified here. Like for example, if I choose normalized input of 0.1, so 0.1 will be output how much? 0.75 or 0.76, right here. So and then the SQNR comparison uniform and mu law quantizer. So let's do that. So if we look at this is the uniform quantization, and here this one is the mu law. So you can clearly see the gap here. That gap is basically, see here the gap, that gap of around 12, 13 dB. This is the penalty, right? This one is the penalty. But now let's move. Here we are. We have nothing. We have no problem here. But we are moving as we moving in this way at minus 10 dB. We are okay. But let's see what is happening at minus 30, minus 20, minus 40, and minus 50 dB. So see here how much is signal to quantization ratio. Let's say let's talk about minus 40. So it is around 12 dB, which is extremely low. Right? Similarly, minus 30. Even minus 30, it is around 24, 25. Let's compare it with mu law. This is our mu law. Of course, there is this penalty, but as we are moving in this direction, right? Minus 10, minus 20, minus 30. So see here, it is keeping its constant value of 30 up till here, till minus 40. It's 37, 38, right? Here. But if we move further, even if we move further here, we are not touching zero. Minus 60, it is above. See, it is minus 10 for uniform. But what about mu law? For mu law, even if we touch minus 60 dB, our SQNR is still around 25, 26 dB. That's why we use mu law or A law, right? Of course, we pay some penalty here. This is that penalty of 13 something dB. But at the end, we are much more better off as compared to the uniform quantization. Okay. Okay. So now let's talk about differential pulse code modulation. We did the pulse code modulation, PCM. Now let's do what is this differential code modulation. So here, if we read here, in DPCM, the difference between the current input sample and estimate of it based on previous sample is quantized and calculated. Well, this is what the difference between DPCM and PCM. In PCM, the difference is here. Input sample and estimate of that is spent instead of sending, right? Yeah, so estimate of based on sample is quantized. So what is this basically in PCM? What we do in PCM? So let's say this means that let's say I am sending this signal. I have here no sample and I give it a value of 10111. Here this is right. So what I'm doing here, I'm sending here 2 bits here are redundant. 2 bits are redundant. I don't need to send back extra bits, right? So I'm sending extra bits. The problem is if the bits are increasing, the bandwidth requirement also increases, right? So, what's the right? So what I can do, I can use this simple differential pulse code modulation. So here, instead of sending like this in PCM, we are sending each sample. We are sending right. So regardless of which we are sending, let's say for example, sample number 1, sample number 2. I'm sending sample number 1, 110. Sample number 2, I'm sending 111. What I'm doing, I am basically sending this is redundant, right? And in here, for example, I'm doing 2 bits. I'm having 2 bits which are redundant. Right? So I don't want to do that. If I want to write that, I can start with differential pulse code modulation. So you can see here the differential pulse code modulation. So what's happening here? what's happening here, we have this, let's say I have this current sample x of n, I pass it here, applies it through a quantizer. Now here I have this pre-reduction filter. This pre-reduction filter, prediction, not pre-reduction, prediction filter. This prediction filter will predict the next value, right? Here it will predict the value, like what is coming, right? It will predict that value, x, we call it x of n, right? That x of n goes here. So of course predicted value and this x of n, they are, of course there will be a difference, right? For example here, why we are having this filter? Well, before labeling between this sample and this sample, right? Here is high, there are high correlations. These signals, like a signal, they are not changing rather flat. They are changing like this, right? But then they are changing slowly, right? So if they are varying or changing slowly, their correlation between two samples is very high. So the prediction filter or prediction filter, keeping in mind this thing, prediction filter predicts. But again, it's the prediction, so we will get some error difference, right? That difference here will go to this quantizer. Of course, this quantizer will round up whatever the error is here. It will decide that. So again, it will also have some calculation error. Now, that is the output, and then for the next cycle, to improve the process, it is here the feedback. Similarly, this predicted value will come here. So that feedback again goes to this prediction filter, which will improve on next time, and this process will continue. But this process will continue with this process. And in real time, again we have this as digital output is coming here as a digital signal with real time. So it will give us some y of n, right? And again here we have the same prediction filter here, and in real time we are having a prediction value here, which will be the value is here. We are comparing both values here. We get some value x of qn, where that x of qn is passed into the prediction filter. In this case, after the prediction filter is so this x of q is fed back here to the prediction filter. This x of q is used for the next value, the next value, the next value. So this is from inner side, and this is real side. This is the differential output modulation. Now, what is the difference between this and PCM? Well, here we send the difference, right? We don't send those like this here. We send the difference. Now let's read. Let's do the mathematics here. So here, the input of the quantizer is the difference between the current sample value and the predicted value. So here, this dn is basically the difference. Here, this dn is the difference between the input current sample and the predicted sample, which is x hat. So here is that x dn is equal to xn minus x hat. Now this dn is called the prediction error. Since it is the amount by which the prediction filter fails to predict the input exactly, of course it's a prediction, right? So prediction can be close to the actual value, but again it is a prediction value, so it will be off. If it's very small, but it will be off from the actual value, so it will create an error. That error we call prediction error. Then the quantizer output y of n will also, okay, so y of n is getting what? Y of n is what? Y of n is here, it is passing, well, this dn is passing through quantizer. That quantizer will also introduce an error, right? So that y of n is dn plus that error, right? Y of n is equal to d of n plus that error is added to the predicted value to produce the prediction filter input. Now, what is x of qn? This x of qn here, what is that? This x of qn is y of n, and this x hat, so here is that x hat of n plus y of n. You plug in the value, you got x of n plus e of n. So the quantized sample x of qn at the prediction filter input differs from the original signal input sample x of n by the quantization error here, right? E of n. Of course, you can see that from this equation, right? This En. Irrespective of the prediction filter complexity, right? So it will be there. So basically, the quantized sample x of qn is the actual signal plus the error, quantization, noise or quantization error. Now, if the prediction is good, the variance of the prediction error will be smaller than the variance of x of n, right? If the prediction is good here, then of course the prediction error will be smaller than the variance of this Dn will be smaller than the variance of x of n. Therefore, a quantizer with fewer number of levels compared to PCM can be used to produce the same quantization error variance. The receiver reconstructs the quantized version of the input sample x of qn from y of n by adding it to predicted value of the current sample generated by an identical predictor here. This here, right? This prediction filter here reconstruct the quantized version of the input sample xqn from y of n by adding it to the predicted value of the current sample. By adding it to the predicted value of the current sample, right? Here. Generated by an identical predictor, which is same as at the transmitter side. The prediction filter is usually implemented by FIR design, right? The prediction value the predicted value x of n is given as here. This is the prediction value x of n is h1 xq n minus 1 h2q n minus 2, and this is this FIR design. Now we have this prediction gain. What is that prediction gain? It is basically equal to this signal power divided by the prediction error power. This is prediction error power, and if GP is greater than 0, we say that the prediction filter is doing a good job. Yeah, he told you. He's telling you